Okay, my friends. Well, the last thing that we have now, after we've done the reading quiz, talk about Le Chatelier's principle, the three different stresses that can be applied to a reaction that's at equilibrium. Remember, and the one thing that kind of gets overlooked and is essential to understanding equilibrium, at that point in the reaction, nothing is happening. You've got some reactants there and some products there. They're not doing anything. It's just sitting there.
Enjoying life.
Right. It's the most comfortable point in the reaction, so it's very comfortable. So you need to disturb the reaction when you want to cause it to shift. And the three disturbances are these. Change the concentration, the pressure, and the temperature. We're in fourth hour again. Brune is kind enough to help us in recording.
He's a camera man.
Hello. So anyway, can something that's burning ever be at equilibrium?
Can something that's burning be at equilibrium? No.
Oh, okay.
Composing?
Burning is a reaction, and so you see the process of the reaction. That's not equilibrium. And yeah, decomposition can come to equilibrium. You can have the reaction proceed, and then when it stops, that's at equilibrium, even before all the reactants have decomposed.
Oh, okay.
Yep.
Do you think it's irrelevant, but do you think it's possible, like, to melt diamond in the future so you can make it later?
To melt it means that you would have to liquefy carbon. And I've never heard of liquefying diamond or carbon. It decomposes, and actually it doesn't decompose, it oxidizes. It would make CO2. But I think it may just sublime. It may go from carbon solid to carbon vapor. I've never heard of liquid carbon before.
Just like diamond, if you melt it. That's it? It's just gonna...
Well, diamond is pure carbon, so it's just a form of carbon. I don't know if you pressurize it enough, what would happen. I've never heard of liquid carbon before.
That is way too much chocolate.
Oh, that's a lot.
You should share.
You guys are very generous. I'm good all year.
I'm so lucky. All that chocolate. You're gonna give us Olays. Yeah, I should.
Yeah.
I can feel it.
Yeah, I need that reading.
You should give us a plus one.
And by the end of the year, I'll have to sit and teach you because I won't even be able to stand up after all that chocolate.
Okay, when we combine up and downstairs.
Good idea. I could use that. Okay, shall we go on? No, Wait, come on.
Why can't we have a party?
Tomorrow?
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 Seriously?
Oh, yeah. Because you're gonna be here at school tomorrow, right? Well, you must be chemistry party. I'm not coming to school tomorrow. She has the panda. Yeah, I don't get a panda. That was so big.
All right, we're
Where's
good.
my panda?
Mohammed, we can't keep doing this.
Sarabi, you gotta choose between a library and
No, no, we're
Well,
gonna have to
actually, I
break.
can get you both.
All
Actually,
right.
just get me Barnes and Nobles.
What's happening?
Yeah.
Propia, where's my panda?
My dad. I think you have panda.
So, all right. Three stresses that can be applied, the first of which is changing the concentration of reactants or products. Anytime you have a reaction equilibrium, remember, there's one container, and both the reactants and the products are in that container. If you add the reactant, I've got this reaction, A yields B. Add reactant, the reaction becomes reactant heavy, and so it's going to shift to the right to get rid of some of that and get Q back to equaling K. Q, remember, changes throughout the reaction, and if you add a reactant, that throws Q off. The chemistry. Oh, no. No, I just post them.
I tried to draw Rudolph really quickly with the marker. I feel bad for the viewer who has to see.
Feel bad for what?
Wait, what?
I just insulted him.
What's new?
Wait, so you never answered my question. Why don't we have a party in this class?
Oh, after the AP exam is over, you can have all the parties you want.
Every day is a party.
Remember, we're done with this curriculum. Go ahead in or late April. So we've got to cram a year of freshman chemistry into college freshman chemistry into what, 7 months, something like that. So we just don't have time. After the AP exam, we can make ice cream, make s'mores, that kind of thing. We can have lots of fun and laugh and smile. But not now. Yes, sir?
So after the AP exam, can I bring in all the Lord of the Rings movies so you can watch them?
Bring on what?
Bring all the Lord of the Rings movies in so that we can watch them?
Yeah.
Oh, cool. Okay.
That's it?
Oh, so like if Q equals K in equilibrium, why don't we just call it Q on equilibrium? And like, I don't get why they put another, like they gave another letter for equilibrium of Q.
Isn't Q when it, like, it's like not equilibrium. It's like
That's right. It's any point in the reaction, you find the Q. And equilibrium point is so special it gets its own name.
Y, K.
See, you should give me my point back.
Hey, we all have first names to distinguish us from our brothers and sisters. Do I call all of you your last name?
You could, but it's hard.
I mean, in this class, yeah, because you all have different last names. But like, would you want your parents to all call you by your last name?
I have an only child, so.
That was a bad example.
You know, actually, I knew this one guy who, and like, he and his brother had the same first name, but then a different last name. So.
Oh yeah?
Yeah.
No, that makes sense.
Wait, what?
Yeah.
Yeah.
I know. I was so weird.
Okay,
I'm so weird out by
that's
that.
different. Are we good with this one? This is now, gentlemen, and shut up.
I feel bad for you.
There's still.
So Tyler's only one.
I do want you to make sure that you know how changing the concentration, adding a reactant, adding a product, removing something, reactant product, causes the reaction to change. If you're not comfortable analyzing the Q number, if you just don't really get Q, and I know there are some out there that don't, just think of it like this. If you add more of A, that makes the reaction reactant heavy. And so it's going to try to get rid of some of that extra reactant to get it back to that equilibrium position. Remember, equilibrium is the point of comfort. If you throw a reaction out of its comfort, then it's going to try to get back to that position. So if you throw more A in there, it's going to react to B.
Why would we do that?
Kind of
Like it's okay at equilibrium.
If you have a reaction that has a small K value, it means it goes to the right a little bit and doesn't make any more product. If you need more of that product, then you have to find a way to shift that equilibrium to make more.
So it's all about the.
Yeah, so you might want to pressurize it or remove product to make more of that kind of thing. Vanadium.
Why do you not have to remove the, or remove a,
Because it's just redundant now, you get the idea of it.
oh,
by
okay, so
that
it
time.
just.
You can remove A, yeah. Yep. All right, next thing is changing pressure. Two things about changing pressure. Number one, if you throw an inert gas, a non-reacting gas into the mixture, nothing happens. Yes, the container feels more pressure, but the reaction, the reactants and products, they're not any different. They're not affected by something that doesn't react. So that's why, that's the one topic that I got the most questions about before the reading quiz is, what about that inert gas? That increases the pressure, and you said that increasing pressure should cause it to shift. But if it's increasing pressure due to an inert gas, that's not going to affect anything. Anything. Yes?
So you need to have a reacting gas in there, or can you just have
Yes.
a gas other than your gas?
No, you have to have something in there that's going to react with either the reactants or the products.
Oh, okay.
Yes, sir?
When you add inert gas, the volumes are allowed to change,
Then it what?
would it affect?
Yes, it would, because you're increasing the volume, and that throws the K off. Or the Q off, I should say. Yes?
But say that you have a delta N, so for example, you have 1 mole of gas turning into 3, for example.
Yeah.
Well, when you increase the pressure, wouldn't it want to take away that pressure and still shift to the left? Or-
With an inert gas?
Yeah.
No, let's say we have a 1 liter container. And we have some reaction to equilibrium in there. If I pump some helium into it, the helium is there, it's going to be bouncing off the walls of the container more, but the helium does not interact at all with the reacting substances in the reaction. So the reaction is not affected by the presence of some helium in there bouncing around. That's it. It's like if I were having class and halfway through the hour, I take a plant and I put a plant over on that lab station. I've just added something to the class. It doesn't affect what we're doing in here, right? It's an ugly plant.
It's ugly, that's why
Yeah,
it's
we're
distracting.
trying to. We
Put that
just
junk
don't
back in.
They're like, ooh, helium.
Right. It's like, wow, we have helium here, but it doesn't do anything with
No,
the
like,
reaction.
Welcome to the party.
Oh, stop. They get excited with the new visitor, right? It's not, those particles are not a group of chemistry students.
Yeah, but that wasn't enough, just so you know.
Okay.
You can leave it.
You guys got a bunch of fitness students. Like, your grade will, oh, never mind. Your grade will go down if you have this.
I don't even know what.
I missed it.
No, I was talking about just I'll forget about whatever I said.
I will miss you, Cole.
We will.
Right now.
You get one guess. Nobody in this class. Ajay.
Ha.
You know him?
Are you sure you have a video that reminds me of Ajay?
He's scared of me. He runs away.
Every opportunity I get, I make fun of Ajay. He's in the hour before yours, and
Wait, why? What do you
he's just fun to make fun of. I don't know. He's a nice kid, and
One of those people, huh?
um,
No pox.
yes, very much so.
Wait, what?
Yep.
He's on tape.
Yeah, well, Ajay knows. He knows. Yeah, if you ever stop into my third hour.
Hey, can you stop punching every time he sees me in the hallway?
Alright, when I say every time I get,
That
no,
kid.
whenever he sees me,
All right, is everybody done with this?
And they go like, dude, what's up? Dude.
Now, I know that this looks kind of scary, but this is a review. Remember in the thermodynamics chapter, we looked at the relationship between equilibrium constant and temperature. If a reaction is exothermic, it's got a positive slope on this, which means, look at this.
I'm gonna sit back.
As the temperature goes up in this graph, the equilibrium constant is going down. This is only good for exothermic reactions. If it's an and if you remember, the slope of this is negative delta H over R. Of course you remember. The slope of this is negative delta H over R, but since this is endothermic, the delta H is positive, the negative of that is a negative slope. So yeah, I mean, there's a lot to remember with this. Just a reminder that for exothermic reactions, heating it up, which is going this way, causes the K to go down. Remember, the temperature is the only thing that actually causes K to change. Other things will cause reaction to shift to get back to that K value, but this is the only thing that will change K. Nick? No, I don't think so.
So are we reviewing everything we learned in the book, basically, for the shock thing?
Well, not everything, but some things, yeah.
I see, the book was confusing.
I don't remember if I told you that the temperature actually changes K. I probably did.
What's the deal
So you,
What's
the what?
the
That they'll change the total pressure, but it doesn't affect the equilibrium. The reacting particles don't affect it. That's what the book said.
Yeah, but like, I don't understand.
Yeah, they used too many words to say it.
Yeah. Diamonds. No, no. White. Okay.
I feel like we learned this before.
This is all from Chem 1.
Yeah, but we don't even anything like
Even dying.
Mr. Morgan, he's just confused. He thinks he's Japanese.
Oh, he is technically.
Konnichiwa! Stop! Wait, why are you trying to... It's the only Japanese That's right. Is it Asian? I get Chinese.
Not much deeper, no. The Shanti, not really. Yeah, it is easy. It is. I expect it. All right, man, we good writing with that?
Like the least
I know
wrong
this is a
person.
full slide.
I I've never even worn like a traditional brown piece of clothing.
Yeah.
What? Hey, is it the brooms? No. Oh, I think that was a magnet. Wait, what happened to those?
Oh, I have like 50 of them at once.
Wait, what was I saying? But yeah, I'm like the least brown person because I've never even worn like those traditional Indian stuff. No.
I'm forced to wear it every time.
I've never worn those in my life. Never.
I'm actually more of like a
No, all sets are easy. And then I've never.
When you take your packet out that I gave you with the example problems on it,
Oh yeah, Mr. Moore. I think I leave all my packets in here because I don't have any. So
Maybe
it's
so.
like,
go to packet number 5.
oh, do you, Mr. Moore? Do you mind?
What's that?
Do you mind?
We don't have 5 packets.
Got number 5 on there?
Yep, got it.
All right.
Okay.
So if I can have your attention, let's go through these together. Let's go kind of quickly. We can get through this, then we'll just be good for the day.
I found it.
Oh, nice. I'm proud of you. Improvement, growth.
What?
So number 5. All right. Number 5. Yeah. For the following reaction in equilibrium, which of the following will shift the position to the right? So 4 of these, well, I don't know. You can't assume the 4 will go to the left, but only one of these is going to cause the reaction to shift right. Which one?
Wait, you're still on this, right?
Shift to the right.
Oh yeah, it's C.
No, it's shifting to the right.
Yeah, it's C because you're taking out BR2, so the reaction shifts to right because you need more.
Wait.
Can we walk through all 5 choices? We're not going to do that for all of these examples, but number 5A, if you decrease the volume, it's going to go toward the side with, it's going to increase the pressure, so it's going to go toward the side with fewer moles of gas. That's to the left. So A would not shift it to the right, it's going to shift it to the left. Fewer moles of gas. B, adding more NO, that's going to make it product heavy, shifts it to the left. C, remove BR2. That removes a product, so the reaction is going to shift to make more. That's our answer. Yes?
Could you go for A again? Because I get C, but no.
Increasing the total pressure by decreasing the volume. Look at me, make the container smaller. The reaction is going to try to make itself smaller, so it's going to shift toward the side that's got fewer moles of gas.
Oh.
And that's the left. D, lowering the temperature. Is this exothermic or endothermic? It's endothermic because the delta H is positive. So if it's endothermic, that means heat's a reactant. And the removing a reactant is going to cause it to shift left. Yeah? That's not what we're looking for. We're looking for right. Oh, what about, I love E's choice. Remove NOBR selectively. Now in C, we didn't remove BR2 selectively, but we did for E. It's just a funny thing. It makes me chuckle. Jesus means to take out NOBR. I don't know why they had to say selectively.
Because you're not taking out all of it, I guess? I don't know.
Yeah, maybe
Well, selectively means only that and nothing else. So, I don't know. It's the same as C. Anyway, removing the reactant is going to shift it to the left to make more. So C is the only one that shifts it right. That's our answer. Number 6. Look at number 6. Try to do this one. I'll ask for you to give me an answer. Don't just blurt it out.
No, a prop. Come on now.
You got that on your camera?
Oh yeah, I'm just holding it up so that people don't have to like,
All right. Remember, there's only one factor that changes K at all, and that's what? The temperature is the only thing that changes K. But specifically, we need to increase the K value. So that means that we need this reaction to move toward the right to increase K. Well, are any of these going to involve temperature moving it to the right? Yes. This reaction is exothermic because delta H is negative. That means that if we remove heat, that's going to remove one of the products from the reaction, causing the reaction to shift right, causing K to go up. Yes?
Yeah.
Try number 7.
So it's A.
Well, for number 6 it was A. Yep. Number 7, same reaction. But so we're going to compress the volume again, causing the pressure to go up. Which side is it going to shift toward? If either. What do you think? D. Right. It's going to go toward the side with 2 moles of gas rather than 3. So it's going to go toward the products. You okay with that? That's how we do Le Chatelier's principle. What about, for number 6, they were talking about adding a catalyst. Did you read in the book about what a catalyst does to the equilibrium? Catalyst will not affect the equilibrium position. It may help to get to equilibrium faster. Because remember, catalyst affects the kinetics. Equilibrium is determined by the thermodynamics, which is well, just the beginning and final energy, not what's going on in the middle. So remember that, because catalyst comes up a lot. Catalyst does nothing to equilibrium, to the position at least. It helps the reaction go faster and get to equilibrium faster, but not to change the position. Yes, ma'am?
So, for number 6, that, you know, like, cause the equilibrium of the compound to increase, do you like the product
For K to go higher, that means we have to have a shift toward the products. Okay? All right. Now, I have one other problem that I want to present, and that is, I have it up here. This one. This is called the 5% rule. I told you about this at the beginning of class. This is a way that we can make our math simpler. So we're done with the handout for now. Don't throw it away or lose it.
Shut up.
Anytime, now listen to this. We've made a few ice tables already. Anytime you have a problem that gives you information about the beginning of the reaction and asks questions about the end, or the other way, if it gives you information about the end and asks you about the beginning. Anytime you're dealing with the beginning and end of a reaction, use an ice table. So we have a chemical equation for a reaction and its K value. We have some information about what's going on at the beginning, and the question is, what are the concentrations of all species at equilibrium? So we want to know what happens at the end. Make an ice table. Let's do that. Now, Crockett, you didn't help me a whole lot here. NOCl yields 2NO plus Cl2. And the K for this thing is 1.6 times 10 to the negative 5th. We make an ice table. What do we know? What are we given to start with?
The equilibrium constant. And
So we know K, yeah?
start.
Do we know anything about the reaction initially, before any reaction occurs? Robbie? Yeah, we know how much of the reactant there was in the container. We know that there were 2 moles and a 2-liter flat. So do I put 2 moles up here in the initial?
Yeah. No.
What does that K mean?
It's a chain.
KC,
Concentration.
concentration. Only concentrations or pressures go in this table.
So that's
Never
one.
moles.
So that's 1.
Wow.
It's 1, right. 2 liters divided by 2 moles divided by 2 liters is 1 molarity. I'm going to use a different color.
Wait, what is
You don't put moles as quantities into an ice table, you put concentrations, because this K is Kc, the ratio of the concentrations. Yes? All right. How much of the products do we have at the beginning?
0.
0. Okay, now the question is, what is this, and this in equilibrium? That's what we're trying to find. We've got to fill in those 3 boxes.
We don't have the K though?
Right there.
Yeah, that's like
Is this reaction at equilibrium initially?
No.
No. Is it going to shift to the right?
Yes.
Are you positive?
Absolutely.
Yes. No question, because we're starting right now. The Q is 0, and the K value is a small number, but it's a positive number, so it is going to shift to the right. Shift to the right a lot, or just a little bit?
A little bit.
K is small. It's going to shift to the right a tiny little bit, and then it's done. It stops. Okay? So, it is going to go to the right. Now, how do we describe the changes here? It's going to go down by some amount. Do I say minus x?
Sure.
Minus 2x.
Let's call it minus 2x. You could say minus x, but over here it's going to have to say plus a half x. I don't want to use fractions like that. I mean, fractions don't scare me, but let's not. We'll do it like that. Minus 2x plus x. Oh, because it's a 2 to 1 ratio. And if I call that x, I got to call that 1/2 x. I don't want to. Yeah.
So just to clarify, molarity always goes up or goes down with relation to the constants of the reaction.
What?
So the concentration of the products and the reactants go up and down with respect to their coefficients.
Yes, in that proportion. Yes.
Yeah.
Or ratio. Yep. All right. So we have equilibrium values now for each of these, but they're in terms of x. So that means that we're going to have to do some work. That's 1 minus 2x, that's 2x, and that's x. Yeah? So, doing the math, we have k, which is 1.6 times 10 to the negative fifth, equals, the numerator is the products. Now this term is 2x, but it's got a 2 coefficient, so it gets squared. So it's 2x quantity squared times x to the first power over 1 minus 2x, and that's got a coefficient at 2.
What is that?
Oh, quadratics.
How's that look? This is not a quadratic. It's a cubic polynomial. You're going to have 3 x's up there.
2x.
Are we hoping to have a shortcut to not have to solve for a cubic polynomial and get 3 roots? This thing is called the 5% rule. I'll tell you why we call it the 5% rule, where the names come from soon. But I'm going to just walk you through this approximation. It's a good approximation. Do you agree, we all said, some of us said, that this shifts to the right, but only a minuscule amount because the K value is so small? That means we're going to have mostly reactants at equilibrium. What can you say then about the size of the x? X is small. Because it goes to the right, but a tiny little bit. So if you have the number 1 minus a very small number, it's still very close to 1 when you subtract, isn't it?
Yeah.
Would you agree with that? Now, what if I have 0 plus a very small number? Can I neglect that too?
No.
No, because any number that x is going to be infinitely more than 0. That's true. So when you're starting at 0 and it goes up by even a small amount, you have to count that amount that it goes up. However, when you're already starting with a number that's pretty big compared to a small number, and you got to subtract a real tiny number minus or from a big number, then that minus 2x right there can be neglected. Because this number is going to be still very close to 1. So that means this term right there, 1 minus 2x squared, because that 2x is so small, it's negligible.
But it's square.
Now in the denominator, it's 1 squared. Instead of 1 minus 2x squared. Now try the math.
That was amazing.
2x.
You're going to have a cubic number still up here, but it's over 1 squared. And I think that's not too bad.
This is 4x cubed.
You are amazing.
No, it's the Zoom dolls.
No,
Wait, so
you
why
are.
is it called the 5% then?
I'll tell you why that part is true in a second. So would you go ahead and find a value for x?
It's 4 times 10
Do
to
the math,
negative
find
6.
x. X equals, Prakya, I'm afraid I'm going to have to erase that.
Go ahead.
Okay.
Okay.
I'll keep something. What do you want me to keep?
The holly.
Deal.
Keep the Christmas tree with the bowling balls on the top. Whatever that is.
That's holly.
What's holly?
Mr.
You don't know what
Christmas tree with bowling balls, fine. That's fine.
Yeah.
You get what? Give me two sig figs.
0.016.
0.016. Wait a minute. Prakya, Artea. Did you make that 4x cubed at the top? 2 squared.
No.
Okay, I was gonna use
Okay, so listen to this. You wind up with 4x cubed on top over 1 equals that number, so solve for x. You got to divide out the 4 and then take the cube root. Personally, when I'm using my calculator, I raise that number to the 0.333 power. That's as good as the cube root. It's faster to me on the calculator.
Or 1/3 power.
Yeah.
Or 1/3 power. Right. Now, that makes this number at equilibrium 0.032 because it's got to be 2x. This number is 0.016. It's just x. Now, what is 1 minus 0.032? Notice this, that this number we had up here was 2 sig figs. It went to the 10th place. This number starts in the 100th place. Do you see how that term is so small it's negligible compared to our original value?
Yeah.
So it was okay. What would we say that this number is at equilibrium then? It's just 1.0.
Whoa. Mind blowing.
Okay, why do we call this thing the 5% rule? Here's why. Because of this. I'm going to write this up here, then I'll show you mathematically. If x is less than 5% of the original concentration, it's negligible when subtracted. So since it's negligible, we ignore it. That's that part right there. That x was small, so it's negligible. Now, read that, and then you're going to have a question. You can go ahead and ask.
What if it's more than 5%?
Oh, that's a good question. Not the one I was thinking of. But if it's more than 5%, then you're stuck not neglecting that, and you got to do the whole nasty math.
But you wouldn't
Cubic
do that twice.
polynomial, find 3 roots, 2 of them are bogus, and find the right answer.
But you wouldn't do it.
Or you can, the book, those Zoom dolls are so clever. They have a method, if this is more than 5%, called successive approximations. Should be fun to look up that. It's in the appendix.
I'll just
So will you ever do that to us, like on test, like on
You
multiple
wouldn't.
choice
Because
test?
you're too nice and you eat chocolate.
Normally I save the chocolate for when I'm grading, so I don't know. It depends on.
today's reading mode.
How.
No, like make it more than 5%.
All right. Now hang on a minute. The question I expected you to ask was this. Nick, thank you. Ask the question.
Water naturally at equilibrium, like has the other 2 ions, but we don't like consider it.
Yes. Yes. Right. That's true. Okay. Thank you, Vanadium.
So how do you know if it's 5%?
Thank you. That's the question I thought that you would be asking.
Yeah.
I said if this is less than 5%, how do you know? Do you have to go through and do this whole problem and then figure out if it was 5% or less? Yes. Make the assumption, make the approximation, go through and find x, then take your x value after you've done all the math and divide it by the original concentration. Trust me, it's worth it to do that math. Usually it will be. I have a general rule for you. If your K value is 10 to the negative 5th or less, generally the 5% rule will be fine. You can
So if it's
you
negative
can
4,
approximate
then
that
it's
thing. What's that?
So -4 is bad.
Sometimes even -4 if that number is high enough. Okay, so here's what we do. When you get an answer for x, you're going to take x, 0.016, over the original concentration, and then times 100.
Amazing.
You're finding what percent that is of that. If that's less than 5%, then the assumption was okay to make. And is the assumption okay to make?
Yep.
What's the percent? What?
1.6.
It's 1.6% way less than 5. How do you like that?
It's
5% rule. You will be so happy to know the 5% rule. Chapter end of 13, all of 14, all of 15, you're going to be using the 5% rule. It'll be your best friend, other than the Zoom dolls. It'll be your best non-Zoom doll best friend.
Yeah. don't want to go to my best friend.
Very quick demonstration. It's kind of a dumb demonstration I want to show you anyway. We're almost done. Yes.
I'm gonna do nothing productive this day. My cousin finished her master's degree in chemistry.
Wow.
And then she plays things way too fast. Okay.
It's so
I
funny.
understand the words you're saying, but I don't understand.
It's really funny. My grandparents were both math people and engineers, like pretty much great math people. My dad's an engineer, my mom's an engineer, my brother's gonna be an engineer, and I'm like biomechanical.
Just for that one, it's so mad. I loved it.
See here.
Sorry, Christina.
Can I have everybody look back here, please? What's that? No. I'm doing it back here because Chinook and Nabil have been so engaged in the lesson today that I wanted to make sure that they were the closest to see, to get the best look at it. Sometimes people are more interested in the stirring than in the actual demonstration, but that's the way it goes. That's a risk I take. I've got a magnetic stirrer in here. Maybe you've never seen one of these before. This box has a motor with a magnet in it. Just drop a magnet that's coated with plastic in it, and it stirs it for you. So when we make your solutions, like for labs or whatever, instead of just sitting there stirring with our hand, we put it in on the stirrer and walk away from it. So anyway, now this is just sodium chromate. If you look back at my chemical equation that's on the board, hydrogen plus chromate ion yields dichromate plus water. I have some hydrogen ions here in the form of hydrochloric acid, and being very mindful of safety.
No goggles.
Yeah, something like that. Here's my other reactant. When I add just a splash of hydrogen ion, oh my goodness. You see what happens there? It's going to shift to the right, and you can tell that it now is not as yellow as it was before, because now it's kind of come to equilibrium. There is some orange dichromate present. Here's dichromate. It's not quite that orange. It's not that yellow either. The more of this that I add, the more reactant heavy it gets, shifting it more to the right and making more orange. See how that goes? Then, what if I add some hydroxide ion to it? Hydroxide.
Then it'll titrate the hydrogen.
The hydroxide is going to find the hydrogen ions and gobble them up. So it's going to remove one of my reactants. And what will we observe?
Yellowness.
There it goes. Yep, that's so good. Yep, yep. So you get some more hydrogen ions in there, and it's going to head its way back to the right, like that. So, you know, this will go back and forth lots of times. And
What if you enter this at the same time? Let's do it right now.
oh, come on, left.
Oh, it's orange and yellow.
It's always in the center.
It's gonna explode.
All right, I don't know what we just learned, but it was good. Yeah, it can go back and forth. That's it. I told you it was a dumb example. At least you got the stirrer to watch. All right, we're good. Oh yeah, if I don't burn something, it's no good.
Yeah, the last one I was here for.
That's it.